So now we are going to discuss the instruction format of 8086. We can classify instructions of 8086 microprocessor in 1 byte, 2 byte, 3 byte, 4 byte, 5 and 6 byte instructions. So let's then discuss one by one. The 1 byte instruction format is, as the name suggests, it's 8 by 8 bit long. Because of the 8 bit, it may have implied register or it may have data operands only. In other combinations, we can also use it as a combination of 3-bit of opcode to specify the register operand, to specify the register. Otherwise, all 8 bits forms an opcode. That means that particular instruction is assumed to be an implicit or implied operands. Three ways in which we can classify the 1 byte instruction format is 8-bit opcode only, or it may have a 7-bit opcode plus 1 bit. That 1 bit is used to define W, that is width, or Z, which is mainly used by REP instructions to control the loop, which we'll discuss later. And the other third category in which we can classify the 1 byte instruction is 5 to 6 bit opcode and 3 to 2 bit register field. So 5 bit, if we are considering as an opcode, then we'll be having 3 bit to define the register field, or if we have 6 bit to represent an opcode, then we will use 2 bit as a register field. For example, this is the case in which all 8 bits are used to define the opcode. This is 0 and this is 7. So all 8 bits are used to define the opcode. The second case in which 1 bit is used to define width of the data, or wrap instruction to control the loop, and the remaining 7 bits, this is 0, this is 1, and 1 to 7, that means 7 remaining bits are used to define the opcode. The third or fourth case in which we can have 6 bits to represent an opcode, this is 6 bit, and remaining 2 bits or remaining 3 bits we can use to define the register fields. So if register field is 3 bit, then we have to choose opcode that is of 5 bit, and if register field is of 2 bit, then we have an opcode that will be of 6 bit. W shows the width of the data. That means if it is 0, then we'll be having 8 bit of data, and if its value is 1, that means we'll be having 16 bit of data. And Z bit we use mainly in the REP instruction, which is used to control the loop. The next 2 byte instruction format, in which first byte specifies the opcode. Opcode is of 6 bit. The other 2 bits are the D and the W. The D is the direction and W is the width. That contains the first 8 bit or first byte of the 2 byte instruction format. That 6 bit, from this to this, we will be having the opcode, and this D bit is for direction, as W bit is for width, to define the width of the data. Now if the direction bit is 0, that means data is transferred from the register, and if it is 1, the data is transferred to the register. So it classify whether we are having the data from the register or we are giving the data to the register. The W width bit. If it is 0, that means we will have the data which is of 1 byte long. That means 8 bit of data, 1 byte. And if W bit is 1, then we'll be having 16 bit data. That means it's a 2 byte data, or in other words, we can also use it as a word. So 0 is for byte and 1 is for word. That W can also be considered as the word. If we see from the previous slide, we have an MOD bit in the second byte. We have REG and we have R/M. So let's them discuss one by one. The second byte have these three fields. First field is MOD. Now MOD is basically define whether the operation is related to memory or related to register. So if we have a register operation only, that means the MOD bit is always 1 1. If it is memory related operation, then we can have three different combinations: 0 0, 0 1 and 1 0. 0 0 is used when the memory mode having no displacement. 0 1 is used when memory mode having 8 bit displacement, and 1 0 we use for the memory in which the 16 bit of displacement is available. The next is REG data. Now this REG, that means we will use it as to define the register field. So we use basically the 3 bits to define the registers, as we have 8 different registers: AL, BL, CL, DL, AH, BH, CH, DH, and AX, BX, CX, DX. That is a 16-bit combination of AL low and high ordered 8-bit data registers, and 4 other registers as well, which is defined as SP stack pointer, BP base pointer, SI source index, and DI destination index. So to define all 16 combinations, we need to use 3-bit, which is to define the register field, and the other bit which is defining the W, which was used as a width bit, but in this case W bit can be used or is used basically to define the register combinations. So if mainly we are focusing on this particular W equals to 0 field, then W equals to 0, and we have REG, that is 0 0 0, we'll be using AL. We'll be defining basically the AL register. If it is 0 0 1, we'll be having CL. Similarly, these 8 combinations, we are moving from AL, CL, DL, BL, AH, CH, DH, and BH. So all 8 combinations are used if we are having one W equals to 0, W equals to 0 bit. Now if W equals to 1 bit, W equals to 1, that means we are having 16 bit of data. 16 bit of data, that means 16 bit registers are used to define the register field. 0 0 0 up to 1 1 1, we'll be having 16 bit of registers. So we have 8 16-bit registers: AX, BX, CX, and DX. Similarly, SP, BP, SI, and DI. So all 8 register combinations are defined using these register field and using W field. Next is the R/M field. R/M is also 3-bit long. If we have 0 0 0, 0 0 1, 0 1 0, and so on to 1 1 1, we can have 8 different combinations. These R/M fields are specifying whether the displacement is of 0 bit, that means no displacement, whether the displacement is of 8 bit, and whether the displacement is of 16 bit. It is mainly used to calculate the physical address of the memory, because these are memory related operations. MOD field, you can see that it is 0 0, 0 1, and 1 0. It's not 1 1. If it is 1 1, will not be having the value of MOD. It will, by default it is 1 1 because it's register operand, a register related operand. We have MOD value that is 1 1 because it's memory related, sorry, register related operation. Now if MOD is not 1 1, that means it is either 0 0 or 0 1 or 1 0. We have different meanings. 0 0 means no displacement. 8-bit displacement, that means MOD will be having 0 1, and 16-bit displacement will be having 1 0. If in these three cases, because we have already discussed this particular case in the previous slide, these three cases from this to this, these three cases, we see that R/M value may have 8 different combinations. So 0 0 0 0 0 1 0 1 0 and so on up to 1 1 1. We have 8 different combinations, and in 3 different scenarios we can calculate whether the offset value, how the physical address of the memory is calculated. So if R/M is 0 0 and we are talking about no displacement condition, that means BX plus SI will give you the total value of the physical address. So BX multiplied with 10 plus SI, source index register. This is BX plus DI will give you the offset in the segment which you are talking about and which the programmer is operating. We can calculate the segment address, and the BX plus SI will give you the offset address, so we can calculate the physical location of the memory. Similarly, if in this particular condition when R/M field has 0 0 0 and we have instruction which contains 8-bit of displacement, that means 8-bit of displacement, that means the 8 will be added to calculate, to provide to make us to calculate the offset address of the particular memory location. And if it is of 16-bit, the same combination 0 0 0, the BX plus SI plus the 16-bit of data, we will be calculating the offset address. Similarly, if it is 1 0 0, then the SI will be the offset address. 8-bit displacement, that means MOD is 0 1, SI plus D8 will be the offset address, and if it is 16-bit displacement, SI plus D16 is basically offset address of this particular physical memory location. If 3-byte instruction format, we have initial 8-bit, that means 1 byte, similar to the previous one. Opcode 6-bit, next bit is D bit, next bit is W bit. The other 8-byte, we have 3 different combination which is already discussed: MOD for 2 bits, REG 3-bit, and R/M, that is also 3-bit. And the third byte will give you the 8-bit displacement. So you can see this instruction format contains 1 additional byte for 8-bit displacement. So the 16-bit, that means 2-byte initial 2 bytes are same, and the third byte is for displacement only. The next 4-byte instruction format is exactly same. The initial 2 bytes are same, and the rest 2 bytes are used to define a 16-bit displacement. Next is 5 and 6-byte format. So initially the 2 bytes are same, you can see that. The other 2 bytes are also same because it is displacement, either it is 8-bit or 16-bit, and then the remaining 1 or 2 byte are used to define the data, the immediate data. If it is of 8-byte data, we use only this. So 1 2 3 4 4 plus 1 5-byte, the instruction will be a 5-byte. And if the data is of 16-bit, then we'll be having 2 bytes for this, these two, 2 bytes for the displacement, and the 2 bytes are for the data. Clear? Now coming to the let's take some examples to clear the all of the doubts. If we need to identify the instruction code of MOV, that is move command, and the data which is moving from the BX register to AX register. That means BX register will have the data which is to be moved into the AX register. So in 8086 we have the opcode of MOV, that is 10010 1000010. Now you can see that it's a 6 byte long. So the other 2 byte is for D and W. D is for direction and W is for width. And you see the data is transferred from register and to register. That means D is 1, and since the data is of 16 bit, because both of the registers are 16 bit, that means W bit is also 1. So the first opcode will be 10001011. This is the first 8 byte, that means first byte, that means first 8 bit. The second 8 bit, which have MOD, and REG, that is register field. MOD is mode of operation field, instruction addressing mode field, and R/M, that means whether the mode of operation or addressing mode is register related or memory related. So it's 2 bit, it's 3 bit, and it's 3 bit, right? So MOD is clear. MOD is 2, that means it is 11, because the data is moving from register, and W as it is of 16 bit, so MOD will be D, this will be 11. Similar to this MOD will be 11. Register, that means we are having the register that is related to AX register. So AX we have 000. So these 0 from the previous slide you can refer. The register field, REG field, having 000 is a R/M, and register code for 000. This will be associated with the AX field, right? And R/M, that field is associated with PX register. That means it is related to obviously register. So for register the W bit is used 0, and since it is related to BX, that means we will be having the code for BX from the previous slide. You can refer. The W bit is 1 and register code is 011. So 0 and 11, that will be the R/M field. So the total code will be 1110, 00 1011, that is first 8 bit, and the other is MOD, that means 11, then REG, that is 000, and the other R/M is 011. So you can see this will be the opcode. You can have 1000, that means 8, 1011, that means 11, that is B. So 8B will be the opcode MOV AX. 1100, that means 12, that means C, and 0011, that means 3. So it will be the 16 bit opcode 8BC3 for MOV AX comma BX. Similarly, you can calculate the instruction opcodes or machine codes for all other instructions. You know the opcode for MOV, you know the opcodes used for AX and BX, similarly all other registers, so you can easily calculate the opcodes or the machine codes of all other instructions associated with um, 8086 microprocessor.